Okay, so thank you very much for the invitation and discussion. So I would like to talk about the MAGO cavity and prospects for high-frequency gravitational wave searches. So just very briefly, this was already mentioned by Sebastian. I just would like to point out that we have this mechanical and EM coupling, but in this initial R&D effort, we are fully focusing here on the how would I point here? Yeah. Here on the mechanical coupling. Just to recap in one sentence, again, something that Sebastian basically already said. So the main basic principle of this heterodyne detection is that gravitational waves are inducing an energy transfer between the two levels of an EM resonator, which are achieved by coupling two identical cavities. And each resonant mode of the individual cavities is split into two modes of a coupled resonator with different spatial field distributions, which are called the symmetric and the anti-symmetric modes. And this is equivalent to a coupled pendulum, which is mathematically also equivalent to two pendulums with slightly different frequencies, which is tunable with this coupling constant. So this coupling constant at the cavity is given by the geometry of the tuning cell, and the original plans for this cavity was to vary the distance between the two cells with pushing with piezos to the two sides of the cavity. So further requirements you have here is what we just discussed, that gravitational waves couple only to modes with quadrupolar symmetry. So you need mechanical modes with quadrupolar symmetry. And also here we have slightly deformed spheres in order to introduce orthogonal field polarizations such that the two EM levels of this TE011 mode have L2 difference. And then basically this also mentioned by Sebastian, you drive your cavity with an external oscillator at the pump mode, and then the gravitational waves is transferring energy from omega 0 to omega 0 plus omega g, and this is resonantly enhanced if omega g is the same as this frequency difference between the symmetric and asymmetric mode. So this is not a new concept. So this initial idea came from the 70s, which then led to the MAGO proposal, which was a proposal for a scaled-up experiment with 500 megahertz cavities. So this was never funded by INFN, but during the R&D activities, there were three superconducting cavities built. The PACO 3 gigahertz cavity, which was a two-cell cylindrical pillbox cavity, which was used as a proof of principle for the experiment. It had a low Q, but it was used to test the RF system and the excitation of the signal mode. Then there was a two-cell cavity with an optimized geometry built. This is the PACO 2 gigahertz fixed cavity, which you see here on the picture. This underwent chemistry and cold test to obtain a measurement of the quality factor for this cavity. And then we have the PACO 2 gigahertz variable cavity. It's a two-cell cavity with exactly the same geometry, but has this coupling cell between the two cavities. So this was never treated nor tested, and this was on shelf at INFN Genoa, presented there as an exhibition. And somehow everybody calls this PACO 2 gigahertz cavity the MAGO cavity, and so I will do this also in the following of my talk.
Question?
Yeah.
Yes. Can you tell us about the size? I mean, and why is that size chosen?
You mean here the size of the cavity?
Yes.
Yeah. So this was simply an R&D project. So it was cheaper, and but later they were planning to have bigger cavities because this was before the discovery of gravitational waves. So at that time they really were pushing as low in the frequency as they could. So that's why the plan was to have at the end really bigger cavities, so yeah, exactly. So after the discovery of the gravitational waves, there were there was a renewed interest in this experiment, especially because it was realized that it's even more well suited for the kilohertz to megahertz range than to the frequency ranges where we expected astrophysical sources. So this work is done now in the DESY Fermilab INFN collaboration. So in June 2023, this year, the cavity came to DESY, where we did a mechanical characterization and RF measurements at room temperature. So this is basically done. I think as of today, the cavity is leaving DESY and should arrive next week at Fermilab, where it will be treated. There will be the support structure and RF antennas will be constructed, and there will be a first cryogenic characterization. So in roughly half a year, then the cavity comes back to DESY. We would like to do cryogenic tests with our initial low-level RF system, and then end of 2024, the cavity will go back to Fermilab, where we will do a first gravitational search with not a specialized, but some existing Fermilab cryostats. And in parallel, the work started also on building a low-level RF system to drive and read out the cavity. So this putting the cavity in a Fermilab cryostat will give you sensitivity somewhere here in this range, in this red band. So what do we have to do if we really want to push this down to lower values? So basically, the main pillars and also the plans for a future experiment to do this is that based on the experience which we have now here with this cavity, fabricate new cavities possible with further optimized geometry. You need to design a low-level RF system to drive and read out a cavity with the highest possible sensitivity. You need to design a suspension system. Sebastian was talking about this dominant noise source to eliminate mechanical noise from environment and ground motion. And then you also have to design a cryostat, which is must be quite special because of course, it needs to have the required thermal properties, but also it has to minimize acoustic noise in the helium bath to a really high level of accuracy. Possibly also due to the smaller size, so on the scale of these experiments, one could have coordinated and synchronized observatories, maybe DESY and Fermilab, and possibly other locations or different frequencies in the future. So in my talk, I will focus here mainly on the DESY activities and plans, and there will be a talk also by Bianca, and I think she will mention more about Fermilab. So the MAGO cavity. So when the cavity arrived at DESY, we did a measurement of the cavity geometry with a laser line scan and also an ultrasonic wall thickness measurement. So here the wall thickness was expected to be 2 millimeter, but yeah, it was rather different. Which is important for the mechanical eigenmodes. And also, yeah, you don't need a laser line scan for this. You see it by eye that the cavity has a dent here in one of the cells. This pointer is a bit weird. I don't know how to point with it, but yeah. Here you have this dent, and if you look into the cavity, you also clearly see this by eye. And also, the cavity is bent. So in the picture above, you see this color coding, which shows the deviations from the technical drawings, but you maybe see it even better with the eye that around the tuning cell, the cavity is pushed in and dented it. So it seems like this cavity was already shaken by a giant gravitational wave. So a delicate part of the cavity is really this tuning cell. So this is fabricated with a turned surface, and here at low radius, the wall thickness is only 1 millimeter. So the cavity has to be braced and restrained in order not to collapse during vacuum, as you see during the simulations. And I think our initial plan will be rather to perform a non-scanning experiment. You see this from the limit plots that you anyway don't gain too much sensitivity by doing the scanning, and this cavity could only allow something like a 6 kilohertz tuning range anyway. The good news is that the cavity is leak tight at room temperature, so there are no damages of flanges or no damage to the flanges or to the sealing surface, so we can really work with this cavity and also do the cryogenic measurements we were planning to do. So we were first measuring the mechanical resonances with accelerometers and interferometric sensors. So you see on the picture these two different sensors. And you see also here displacement of one of the mechanical resonances measurement. So these were really difficult to interpret, I have to say, and we got a better understanding with simulations. What you see here on this, in the simulations on the bottom is that this dent in the cell is causing oscillation maximums in vibration eigenmodes. And if we plot now all the vibrational eigenmodes, then you see here in this plot that there are many more and densely populated mechanical normal modes with a distorted detector. So what we call in the following ideal MAGO is the MAGO from the technical drawings, and the scan MAGO is the MAGO which we measured with the laser line scan. So in the ideal geometry, you see this, the lowest quadrupole mode is here, which has a special role, as also Sebastian explained, and it's nicely isolated, so this is not really the case anymore with the real cavity. This you saw also here with the simulation of the coupling coefficients or the overlap factors, as Sebastian called them. So on the left plot, you see the mechanical AM electromagnetic coupling. So here only versus the frequency of the mechanical resonances. And so here only the modes, only the quadrupole modes are different from zero. And you see there are only a few of these blue dots. Then the gravitational wave mechanic coupling in the middle plot, there you see that basically this one of the lowest quadrupole modes has the strongest coupling. So in the product, you really see that there is one mode, one configuration, which is driving your sensitivity. So now with this distorted geometry, there are several multipoles with quadrupole fractions. Otherwise, the plot would be zero, which you see with the red wiggles. And there is not a clear lowest lying dominating quadrupole resonance like with a clean ideal geometry. Then we did some RF measurements at room temperature, and they were also not what we initially expected. So if you look at the left, there is what we simulated is that you have, for example, at 2.07 gigahertz, you have two modes, which are again very close by frequency, such that if you do a warm measurement, your Q factor is very low, so you are not expected to resolve the two peaks. And similarly, then at 2.1 gigahertz, we have the TE011 mode, which again we expect delta omega by 9 kilohertz. So this is again something which we are not able to resolve at room temperature. And if you look at the measurement here on the right, which is showing the transmission spectrum from one cell to the other, then you see that at all of these frequencies, we are really seeing two peaks. And at the frequency where we would like to detect the signal, there is a frequency difference of 1 megahertz between these two peaks. In order to understand what is going on, we were shortening the cavity such that you really can measure simply one cell. And if you look at the absorption spectra, then you see that these separated frequencies are still present. So it's clearly what we are seeing is that the eigenfrequencies of the two cells, they do not match. And so this is not what we wanted or expected. You remember this with the coupled pendulum, how the experiment should work in principle. So in order to understand this a little bit better, we modeled the two MAGO cells as an inductively coupled LRC circuit, and which was driven by an external oscillator on one side. So this is basically like the MAGO setup. And you see here the equations of motions. You can define the coupling strength and the single cell eigenfrequencies. And if you solve this coupled equation of motions, then you can plot a solution in frequency and time domain. And we were choosing here this omega, which we were observing, this 1 megahertz, and a coupling coefficient, which is typical for Tesla cavities. And you see that here in the frequency domain, you still see nicely the symmetric and anti-symmetric modes. On the bottom, you see the solution in time domain, which is very nicely showing why we call this symmetric and anti-symmetric modes. So here in cell 2, the anti-symmetric mode is shifted by pi, which is also used later in the signal extraction. I will come back to this. But then if we start to lower the coupling parameter to smaller and smaller values, then you see that we are slowly arriving at a picture which is very similar to what we actually measure. And if you do just some tentative fits, so this shouldn't be taken too literally, then we even recover some parameters which we expect to have. So with the delta omega Q factors at room temperature, however, a coupling constant which is really very much smaller, 10 to the minus 5. Now, this V coupling is unfortunately inherent. The V coupling is also giving the operational frequency which we would like to have. Yeah? So because it's simply given, it's proportional to omega pi minus omega 0. So if you would like to operate at a megahertz range or smaller, then you need a V coupling of 10 to the minus 4 or smaller. The other thing which we observed that if you have this coupling configuration with a large delta omega and small coupling, then you have a phase shift here in the antisymmetric mode, which is, however, then vanishing if you go to the superconducting phase. But you also have a low amplitude ratio, which I show here with circles. So this is limiting, unfortunately, the sensitivity, because you have, for example, for the mechanical overlap factor, you have you multiply the fields from the symmetric and the anti-symmetric modes, and also the largest amplitude is limiting the operational power, which then you use for all the cells in the cavity. So this can be recovered by bringing delta omega closer together. So if I make the same plots now for a delta omega of 1 kilohertz, then you see that both problems are going away, and also the amplitudes are now much more similar. So we are currently working on simulations to identify the origin and possible tuning knobs we can do with this cavity, maybe a mechanical or a dielectric tuning. It also turns out that some tuning is practically unavoidable. So because single cell eigenfrequency differences are also expected for close to ideal geometries, which you can calculate with this simple formula. So for gigahertz cells, a relative difference in a radii of 0.1% will already lead to a delta omega of 1 megahertz, which is also roughly what we see with the wall thickness measurements we have. So maybe you can go an order of magnitude better in the fabrication precision, but probably not 2 orders of magnitude. And you can plot, for example, here the coupling coefficient versus the frequency difference. And so basically you saw if we would like to be in this frequency range, then we need coupling coefficient or individual cell resonance differences of kilohertz. So this was also this equivalent circuit study was also validated by comparing to a simplified MAGO geometry, where we vary the coupling cell by simply the distance between the two cells, and we see a very good description. So how can we control the cavity and detect a signal? So there are two similar concepts one could apply. So the original MAGO's readout was done with a so-called magic T. So you see here in the loaded mode and the signal mode in the two cavities, you see this phase shift in the signal mode, as I was mentioning before. So the original idea was there to shift the signal phase of one cell with this magic T by pi, and then if you add up the signals, what you see here on the left with this magic T, then the loaded mode cancels and the signal mode gets amplified. So this only works well with similar, if you really have similar amplitudes between the cells. We are exploring now another method, which is called carrier suppression interferometer, where you shift the driving signal here, P in, by a phase by pi, and you decouple it from the cavity, and then you shift it by pi, and then the loaded mode cancels with the driving signal. This is the picture you see below CSI, and this is less sensitive to amplitude differences. So recently, the DESY low-level RF team, they established a 60 dB improvement of the detection noise floor at 1.3 gigahertz in a laboratory-controlled environment. So this matches very well the MAGO requirements and conditions, and we try to apply this technique. Here, it's good to have a high RF field amplitude, which is also good for a better sensitivity to gravitational waves. And then the excited signal by the gravitational wave is mixed to the driving signal with an offset frequency of 10 to 100 kilo range. And this is also something which is roughly what we are looking for. So we have a preliminary designer for low-level RF architecture. So the current R&D is by the cavities at Fermilab, that we use a FPGA-based cavity simulator to develop the low-level RF and CSI system, and then set up a CSI at 2.1 gigahertz, and then integrate it with our low-level RF system. So this sensitivity which I showed you on the previous plot, so this was really so far only achieved in a laboratory environment. It will be now the first time that it's applied. And then when the cavity is back, then we would like to have a test design with one CSI and a cold RF test. So in the last 5 minutes, just briefly mentioning how could a future experiment look like. So at DESY, we have this cryo platform at here north, which is a possible realization of dedicated high-frequency gravitational wave experiments. So it's 30 meters underground. It has a distribution system of liquid helium at 4K, and you have a supply up to 3 experiments. So, for example, ALPS is also down here, and the MadMax experiment should be also down here. It's currently in construction, and we expect operation from 2026. We need a dedicated cryostat for this experiment. Of course, the more trivial part is to exploit the advantages of RF superconductivity, but you also have to avoid any acoustic noise in the helium bath. And you can get noise at this level, which we really would like to avoid. You get noise from thermal dissipation, from pressure fluctuations, from seismic and environmental noise coupled to the liquid. And if you look at this plot at the right, this helium phase diagram, you can have helium in a liquid or a superfluid state, and there are several experimental setups which are using all these different configurations of liquid and superfluid helium at different pressures. And it looks like that for this experiment, the best would be to use pressurized superfluid helium at 1 bar and 1.8 Kelvin. So this is basically the red dot, which gives the best thermal properties and also minimizes the noise from the helium baths. So you have a high specific heat and thermal conductivity. The specific heat is even higher if you are close to the lambda line, so you don't need to go much more down in temperature. You have a low sound wave speed, such that any acoustic noise is not coupling as strongly to the cavity. And you have a high mechanical quality factor, and at 1 byte you avoid bubble creation. So this is a concept from the original MAGO proposal, which we revisited, and it really looks very sensible. So you start here with in the reservoir up there with saturated helium here at 4.2 Kelvin. Then you pump this with a pump here to go down in temperature to 1.8 or 1.5 Kelvin. So yeah, then you have saturated helium, and this is cooling then the cavity with a heat exchanger, such that you really don't have helium flow around the cavity. And the vessel, which is where the cavity sits in, this is actually, it's not hell, it's helium-2, so the cavity is sitting there in this pressurized superfluid helium. So we started with the design of a cryostat, which I show here just a possible flow scheme to his host in a DESY cryo platform. And what would be important to elevate this entire part where you have the reservoir and the pumps, to elevate and outsource these to maintain pressure and also minimize noise. And there is, for example, the Gersemi vertical cryostat at Freya, which has a similar design concept, so it will be interesting to talk to these guys who made this cavity. My last slide is just on a suspension system. So this is also could be inspired from LIGO Virgo concepts, but the requirements are by far not as strict as you have, because the pendulum resonance will be on the hertz range, and so if you measure in the kilohertz megahertz range, then you have this strong natural damping. So it will be probably enough to have 1 or 2 levels of pendulum with leaf springs for vertical damping. We need to minimize mechanical shortcut of connections, and yeah. So we also started to estimate here what is the noise damping we need to achieve. This plot here, for example, shows the upper limit where the upper limit of this plot shows how much the wall displacement RMS should be such that the mechanical noise is smaller than either the thermal or the amplifier noise. And then by measuring then ground motions in a cryo platform and also vibrations in the cavity, I mean, there are accelerometers which go down to 77 Kelvin. You cannot go until the cavity, but one of the isolation shields, you could estimate the required damping. So in general, we are working on a more realistic estimate of all the different noise sources to gauge the noise suppression requirements we have to find. So let me just wrap up quickly. So with the discovery of gravitational waves, there is a renewed interest in the heterodyne detection method with SRF cavities. So especially this broadband sensitivity is tantalizing that Sebastian was discussing. We use the existing MAGO prototype cavity to gain experience and design further optimized cavities. The low-level RF system development is on the way. We have to address the cryostat and suspension design next. And it's still a long way ahead to reach projected sensitivities, but one could aim for a conceptual design report in 2-3 years for a future experiment. And I think the moderate size of the experiment is also quite attractive, which would also allow for several synchronized observatories. Thank you very much.
Thank you so much.